Yeah, yeah.
Okay, so we start with Dean.
Sure. Hi, my name's Dean DeVito.
Hey, my name's Adrian Molinari.
My name is Andrew Costin,
I'm Kevin Chitaho. So what do you?
and we are Team 5.
Woo!
So for our goal, it was to design and produce a car within specific regulations with the smallest drag coefficient to be tested in a wind tunnel and then logged in LabVIEW. Alright, and our strategy was to use a 3D design software such as CAD or SolidWorks and create a shape as aerodynamic as possible within the mandated geometry given to us. Then we gained access to a 3D printer to obtain a physical body to be used with the provided wheels and axles.
Okay, so for the design process, we chose SolidWorks because two of the members in the group had already used it before, and for the actual shape, we wanted to copy the geometry of a rocket or a teardrop, even though we had to include a cabin.
So our first result had a little bit more corners and edges than we originally preferred. Since that prototype, we tried rounding as much as we could within our abilities in SolidWorks. Further optimization included increasing the diameter of the axle holes, as the original ones were a little small, causing it to seize, and we saw examples where the larger ones rolled much smoother. We also increased the depth of the loading area, expecting to carry something, although that was not necessary. Liars.
So I bet you're all wondering, why is this important and what are the significance of this? Well, I'm here to tell you about the calculations. We have drag coefficient. And with this drag coefficient, we have drag over the area multiplied by dynamic pressure. On top of that, there is a drag force. That force will be equal to dynamic pressure times the coefficient of drag multiplied by the area. With that said, we include Reynolds number in our calculations, it being density multiplied by airflow velocity multiplied by length, all over air viscosity. The drag coefficient is also inversely proportional to dynamic pressure, and we took into consideration the increasing airflow velocity that will increase Reynolds number. So how is this used in the real world? This knowledge can be used to develop yourself in mechanical engineering and aerospace engineering. So you can study the forces acting upon mechanical equipment, machinery, and this can be studied by computational fluid dynamics. Just like how we use a wind tunnel to measure the drag in our vehicle model, this can be used to study the forces acting upon an airfoil and the forces that it's withstanding while it is in a wind tunnel. And the same method can be used for cars and like NASCARs to test how aerodynamic they are and how to reduce the drag.